Okay, this is Anthony Priscilla, and today in trigonometry we're going to define inverse trig functions, something we've used since very early on when we were working with right triangles. Anytime we hit that little sign with the -1, it's sort of hard to see that on the projector. When it's recorded it's very clear, but it's the projector up there. Little sign with the -1, cosine with the -1, tangent with the -1. You may not be able to see it out there, but you can see it on the video. We used those earlier this semester at the time of the first test when we were solving right triangles, but we've never defined them yet. And so we're defining the 6 inverse trig functions today. I sort of want to remember or review a little bit about inverse functions from college algebra. So this little handout I have, it's under document sharing, and I'll hit the major parts. A function has no repeated x's. Oh, what I have right here I'll have under document sharing so that y'all can, if you're curious about more detail of inverse functions. But basically a function has no repeated x's. Every x value gets only one y value, no repeated x values. We said a function is 1 to 1 means no repeated y values. A 1 to 1 function has no repeated y values. Now, if we were going to have a function and its inverse, if we want the inverse to be a function, it's got to be 1 to 1. For instance, if I just write out a little function as a set of ordered pairs, like this one right here, 2, 10, 3, 15, 4, 20, 5, 25. This is just a little basic algebraic function. If we're going to find the inverse, we would switch the x and y's. That's what an inverse does. It switches the x and y's. And this is how we define it all in college algebra. An inverse switches the x and y values. See, in this first function up here, notice it was a function because there are no repeated x's, and it's a 1 to 1 function because there's no repeated y's. When we switch those, this is a function. Why? There are no repeated x's. In order for an inverse, in order for an inverse to be a function, f must be 1 to 1. If the original function has repeated y's, notice, if we had f defined like this, 2, 4, 3, 9, -2, 4, -3, 9. This is a function. There are no repeated x values. But f is not 1 to 1. If we found the inverse by switching the x and y's, are we going to have a function? If you go through here and switch these x and y's, I'm not going to write f with the little -1 because it's not going to be a function. You actually switch the x and y's. Is this thing a function here? No. Because now it has repeated x's. So in order for a function to have an inverse function, that function must be 1 to 1. In college algebra, we talk about the horizontal line test. A graph of a function, in order for it to be 1 to 1, no horizontal line should intersect it more than once. If a horizontal line intersects the graph of a function, let me move this up. More than once, the function is not 1 to 1. So here's a question. Are trig functions, thinking of the graphs, are they 1 to 1? Let's look at the graphs of some of these. Let's see. Here's one. Let's look at the graph of y equals sine x. Oh, some of y'all writing this down? All I'm doing is just setting it all up and try to justify why it's going to be defined the way it is. If we look at the graph of a sine curve right here, is this 1 to 1? It's certainly a function. All the trig functions are functions, but is it 1 to 1? Let's look here. Does the horizontal line, can you draw a horizontal line that intersects the graph more than once? Yeah, so this thing's not 1 to 1. Okay? Well, could we look at just one particular part of it and find a part that would be 1 to 1? Like if we were going to trace along and try to figure out a part that's 1 to 1. Like what about going, if I went from 0 to pi, this part right here, is this 1 to 1? Wait. Right here. This little part here, it looks sort of like a parabola. Nuh-uh. So, but what if we went from pi over 2 to maybe 3 pi over 2? Is that part 1 to 1? Yes. It's sort of up to us which part of the graph we're going to use, but we're going to use the part that every other trig book or course has ever used. Instead of saying pi over 2 to 3 pi over 2, we're going to restrict it to just pi over 2 to negative pi over 2. This part right here that I'm darkening it. So we're going to look just at this part of the graph. Is this part that I've drawn in black from negative pi over 2 to pi over 2, is that 1 to 1? Yes. In fact, I think I have a graph of it. Let's see. Right here. Don't look at that. Look just. Here it is drawn. This is the black region, which, you can't really see. Maybe. Okay. The thing that I drew in black, here it is blown up really nicely. From negative pi over 2 to pi over 2. Notice, this is 1 to 1. So that's going to be the interval that we're going to have to use when we go through switching our x's and y's. Here's an xy table. An inverse function is going to switch those x's and y's. And let me just go ahead and state how we're going to define it. I have little documents, some document sharing, showing these little graphs here and so forth. But I want to actually, I feel like I need to write something out. So here's how we're defining. We're going to use two different notations for the inverse trig functions. We'll use the little -1 notation, or way before people could easily type exponents, publishers wanted a way of being able to write these things without that little -1 exponent. I don't know if surely all of y'all are way too young, but I remember my father having a manual typewriter where you had to roll the paper. Oh, you want to make an exponent, you've got to move that paper up a little and stuff. But modern word processors, it's pretty easy to type those little exponents. But before then, publishers wanted a way of denoting them without having to type in. And so they chose arc sine, arc cosine. I'm surprised they didn't just use I and V, but I and V for inverse wouldn't have, you can't say it well. I and V sine. So they use arc, meaning inverse. So that's all going to be our little inverse function notation. And here's the definition. Y equals inverse sine x means sine y is x. The thing that comes after the trig function, that's the angle. What we're doing with these inverse trig functions is we're reversing these ordered pairs here. The x values are these numbers here on the unit circle. The y values are going to be the angles. We're reversing those. Now, we've got to make sure that the function's 1-to-1. Therefore, it means it and y, how do we say is between negative pi over 2 and pi over 2? I'm going to say it like this. Y is in this interval from negative pi over 2 to pi over 2. This restricted interval that we're going to be using is going to be important. I want to go ahead and justify which intervals we're going to use for which trig function before we actually start doing some problems from the homework. Let's think about, so for inverse sine we use negative pi over 2 to pi over 2. Just remember that. It'll be significant in a little bit. What about, let's look at our graph for cosine and decide which little interval will we look at. Well, would negative pi over 2 to pi over 2 do it here? No. Okay. In fact, that wouldn't be 1-to-1. So could y'all think of an interval?
Just 0 to pi.
Yeah, just 0 to pi. This is the nice thing. 0 to pi. This little black part that I've drawn here is 1-to-1. And I have it drawn bigger. Again, if you're trying, this isn't something you need to try to write down. I have all of these available. The stuff that you need to write down will be these definitions. Inverse sine is going to be using the interval negative pi over 2 to pi over 2. What about inverse cosine? Y equals inverse cosine x means cosine y is x, and y is in what interval? This one's 0 to pi. You're going to have to remember inverse cosine is the 0 to pi one. You have any idea how to remember that's the 0 to pi? Without thinking of without doing it the intellectual way. Thinking of the graph and restricting the domain so it's 1-to-1. If I point here and I point there, see what I'm saying? Yeah, it has the 0. Cosine, the O, the 0. So maybe you can remember that that's the 0 to pi. Over here, for inverse sine, there wasn't a 0 in it. So it's the negative pi over 2 to pi over 2. For the other two that we're going to define, inverse tangent and inverse cotangent, that same pattern holds. For inverse tangent, what domain are we going to be using? What are we going to restrict it to? If you had to guess, inverse tangent, are we restricting it to negative pi over 2 to pi over 2 or 0 to pi? Yeah, negative pi over 2 to pi over 2. There's no O in it. But inverse cotangent, it's 0 to pi. And why are those? Well, if you look, these are the nice ones. The inverse tangent. You see, if you look from negative pi over 2 to pi over 2, isn't this already 1 to 1? Yeah. So that's all we need for that. Just use the interval negative pi over 2 to pi over 2. And what about for a cotangent? 0 to pi. It's 1 to 1. So to complete these definitions here, I'll write it right here. Okay. So y equals inverse tangent x means tangent y is x and y is in. Now it's a little formality, but I want this to look formally correct. These square brackets mean including the number. Well, y can't actually be negative pi over 2 or pi over 2 because the tangent of negative pi over 2 and pi over 2, that's undefined. And so, you remember your interval notation? Putting parentheses mean y can't actually equal those. And for inverse cotangent, it's the same thing. Cotangent y is x and y is in. What am I about to write? Am I going to put a parentheses or a bracket? Parentheses 0 to pi. Sounds much worse than it actually is. Let's see. Did I bring a unit circle with me? Maybe I should take a break and go get y'all a blank unit circle. Just so you can, have y'all forgotten how to fill those things in? Because it's going to be sort of significant. Yeah, I'll just take a break right now. And important stuff. What's the important stuff right here? Oh, I wanted to get one. I had one that was already filled in.
You want one?
From us. Oh, do you have one? I'm going to destroy it with writing on it.
I don't care.
Oh, okay. Thanks. I meant to get one, but I guess I lost it. Oh, the bond passed, and we're going to get a new math building, and I'm going to be sort of sad if my classroom in the new building is
the bond passed?
false. The president sent out an email saying it passed. I haven't heard the news, so did it pass?